Okay, we have mentioned several times along the way in different courses that ocean takes up 93% of all the additional heat that is being trapped because of the increased greenhouse gases and the reduced energy output to space, which is what causes global warming. And because the data are sparse, and especially as you go back in time, you don't have deep ocean data and so on, the estimates of where and how the heat uptake happens and how it is transported end up being different in different products, and this can matter a lot even in coupled models where the energy imbalances can create the so-called drift, where as you keep integrating the models forward they have an energy imbalance at the top of the atmosphere, which has nothing to do with the greenhouse gas forcing or volcanoes or solar forcing and so on. These drifts can be problematic. So this is a valiant effort to try and constrain an ocean model as best as possible with all the data going back to the pre-industrial time, and try to explain how and where the ocean heat uptake actually happens. The model details are kind of hairy in terms of wanting to make sure that the model is constrained properly, so I won't go into those details, but you definitely should read up the paper if you want to get into those details. Just reading the abstract, since the 1970s the ocean has absorbed almost all of the additional energy in the Earth system due to greenhouse warming. We know this. However, sparse observations limit our knowledge of where ocean heat uptake has occurred and where this heat is stored today. Here we equilibrate a reanalysis forced ocean sea ice model. The reanalysis means you are blending data with the model with data assimilation techniques that try very hard not to jerk the model around and so on. And equilibrate means when you start integrating the model, the initial conditions of integrating the ocean for a long time so that it has reached some sort of a statistical equilibrium is very important, so that when you add forcing on top, then the trend you're tracking is actually related mostly to the forcing anyways. Okay, so here we equilibrate a reanalysis forced ocean sea ice model using a spin-up that improves on earlier approaches to investigate recent ocean heat uptake trends basin by basin and associated separately with surface wind trends. So the global warming creates what are called dynamical responses where winds change, and thermodynamic responses where temperature, humidity and radiation can change because of the various feedbacks and so on. Obviously they are not completely independent, but nonetheless the processes can be understood better, especially for the ocean which is forced from the top, in terms of momentum forcing change, which can determine how deep the heat goes, versus surface flux changes, which can determine how much heat is coming in at the top and where it's being taken down by the thermohaline processes, for example, okay, or thermocline ventilation processes. But these are words you have to go and learn from other podcasts. Wind and thermodynamic changes each explain 50% of the global ocean heat uptake, while the Southern Ocean forcing trends can account for almost all of the global OHU. This OHU is enabled by cool surface temperatures and sensible heat gain when atmospheric thermodynamic properties are held fixed. So you can see where the sensitivity of uptake comes from by fixing the winds or the thermodynamic properties like temperature, humidity and radiation, while downward long wave radiation dominates when winds are fixed. Okay, so this OHU is enabled by cool sea surface temperatures and sensible heat gain when atmospheric thermodynamic properties are held fixed, while downward long wave radiation dominates when winds are fixed. These results address long-standing limitations in multi-decadal ocean sea ice model simulations to reconcile estimates of ocean heat uptake, transport and storage. I think I may have a little bit of wind here, so let me stop the fan a little bit. Hold on a second. sorry about that. So these are complicated figures, but basically it gives you a sense of what they are doing. They're using some observation-based product, and they're taking an ocean model and creating data simulated reanalysis product. But since we don't have the forcings back in the beginning of the Industrial Revolution, what they do is they take a decade of 1961 to 71, where we have a very good, well-constrained forcing products, and there is well-known trend that occurred over this time. So they repeat this forcing on the model to reach equilibrium, and then they take out the trend of minus 0.133, or the trend of 0.133 degrees centigrade, which happened over this period. So you can see that this light blue line here gives then a long-term equilibrated simulation as an initial condition for various other simulations. So there is a pre-industrial spin-up period where a model is equilibrated, which can matter a lot to remove the drift, and then there is a transitional period where the greenhouse gas forcings ramp up, and then there is a hindcast period where the heat uptake has accelerated, as you can see, and we want to get a better constraint on this period as to how and where the ocean heat uptake has changed. The transport and the storages that go with it have changed as well. So there is a pre-industrial spin-up and control in this light blue line, transition spin-up, which includes all the forcings, and then repeat decade, which is another experiment looking at the repeated decadal forcing to show how the full forcing and that is the hindcast simulation and repeat forcings change over time. And this is a global ocean heat content during the spin-up. So these are model years, not actual years. So starting with year 0 of the model, which is initialized somehow like a geostrophic balance of a climatological temperature and salinity distribution and so on. And you can see that as the model is spun up, the pre-industrial repeat decadal spin-up has a spin down in the heat content in 10 to the 25 joules. Here we were looking at degree C in surface temperature anomalies during the spin-up, and you can see this focused period of analysis here for the Industrial Revolution to the current. The drift still exists in the spin-up model, but then you go with the constrained transient run and the hindcast run to look for processes that determine where and how the ocean heat uptake happens. As I said, these are kind of technical details that you may or may not be interested in. I'm kind of leading to the last figure, which is a nice summary. So this is the recent global ocean heat content anomalies in observations and hindcast model simulations. So in the top panel, we are looking at how the volcanic forcings affect the surface forcing of the ocean and the heat uptake, transport, and storage. So there is a reanalysis product which is up here, and these are in 10 to the 23 joules or petajoules. Sorry, I should be careful. That is not peta, that is zeta, I think. Okay, just check. And there is an observational product which is quite a bit different, and the differences remain constant almost after some time, but this is not a small amount considering this is 10 to the 23 joules. Okay, CMIP 6 models near observations because they keep in mind these observations in various ways. They implicitly feed into the models. Access OM2 repeat decade spin-up, which is the model reanalysis approach used here. So it's way down from the other reanalysis products. OMIP2 is down here with multi-model mean plus minus 2 sigma de-drifted. So the trend is the drift during spin-up is taken out, and access OMIP2 spin-up de-drifted. So various ways of doing these things, but you can see the comparison of the Argo period ocean heat content trend compared to access OM2 heat content trend has many similarities, but there are also substantial differences. So despite all the exercise of spinning up and constraining the transient and hindcast runs, you can still end up with differences, but one should remember that Argo is for a very short period and its coverage itself is not that dense anyways, so we have to just keep the challenges in mind rather than worrying always about the differences. Okay, and this is only looking at the top 2000 meters, so you can imagine what happens if you go to deeper depths. This is a simulated global and regional ocean heat content changes due to thermal and wind stress and due to regionally constrained atmospheric trends. So the forcings are then constrained by other methods in terms of fluxes being given to the model, and then there are these experiments of holding the winds constant and the thermodynamic variables constant. I won't go into the details here, but you can see the hindcast simulations again, looking at full forcing, thermal only forcing, wind only forcing, and added thermal plus wind only signals. You expect some differences because the two are not linearly additive in that sense, and these are the hindcast simulations again for full forcing. So this is the full depth ocean heat content anomalies, and A is the time series of full depth global ocean heat content anomalies in the full forcing simulation when only prescribing surface winds and only prescribing thermodynamics and so on. In B, the time series for the hindcast simulations where combined interannual wind and thermal forcing is applied only over the Southern Ocean. So the idea is to say that Southern Ocean trend forcing can explain almost all of the global ocean heat uptake, which we will see in a minute. So the basin scale differences of wind forcing versus thermal only forcing are compared here. Again, global OHC, Southern OHC, Pacific, Indian, and Atlantic OHCs are looked at, but it's better to just go to the conclusion. These are the ocean heat uptakes and related profiles, and again the full forcing simulation, wind only, thermal only, and surface temperatures being shown here. We have talked about how Southern Ocean is a channel, so wind forcing can spin up the ocean quite a bit. Much more energy can go in compared to other basins which are restricted by eastern and western boundaries, so the amount of energy that wind can put in can be limited, and this allows Southern Ocean to keep taking the wind forcing deeper, which means surface warming can also go deeper, and so on. So those kinds of details have to be worried about when you look at the sensitivities of regional heat uptakes, because those then determine where the energy is stored and where the transport is taking the heat, right? So let's just summarize. So this is the transport in 10, or the numbers in 10 to the 21 joules per year. This is the heat uptake in the reddish arrows. Blue arrows are where the ocean is losing heat, and the black arrows are where the ocean is transporting heat. Immediately you can see that the fully forced simulation shows that the Southern Ocean has an uptake of 6.9 times 10 to the 21 joules per year. Indian Ocean has a small contribution, and there are transports obviously out of the Southern Ocean into the Indian Ocean, into the Pacific Ocean, and into the Atlantic Ocean, which are consistent with the thermohaline circulation, deep water formation, and this cooling hole, which we have discussed elsewhere, have to be explained by heat loss, and the heat uptake here has to be explained by the heat storage and the heat transport. So you can look at the various numbers here. There is a northward transport in the meridional circulation of the maritime continent as well. I'm not going to go into the not going to go into the details, but let's read the caption anyways. Schematic summarizing this is a schematic summarizing anomalous global ocean heat uptake, heat loss, and heat transport over the last half century in different historical simulations. The spatial patterns show ocean heat storage rates in the full forcing, where all atmospheric forcing fields evolve over time in 10 to the 8 joules per meter squared per year. So red colors are where the heat storage is happening, and this is a strong hotspot of ocean heat storage loss. So that explains the surface trends we have looked elsewhere, where there is a warming hole here, and of course there are lots of spatial variability in the Southern Ocean because of its high spatial variability in terms of eddies and so on. Nonetheless, there is large heat storage here, and there is a large heat storage here in the North Atlantic into the North Sea, Norwegian seas, which is obviously bad news for the Arctic, for the heat transports involved there. Okay, the global ocean is divided into the Southern Ocean and the Indian, Pacific, and Atlantic basins, as we saw before. The red and blue vertical arrows into and out of the plane show the basin integrated heat uptake and heat loss rates in the full forcing. So that's the left arrow here. Wind only, so left arrow, wind only. Sorry, in each case I said it wrong. So there are full forcing, wind only, and thermal only forcings involved in these arrows. Okay, wind only, thermal only, full forcing, wind only, thermal only, and full forcing. These are in the same sign. So ignore what I said before as a screw up. Okay, so here again, wind only, full forcing, wind only, and thermal only forcing. Okay, so same for the transports as well, from the Southern Ocean into the Pacific, into the Atlantic, and in and out of the Indian Ocean. The black arrows show the heat transport rates in the same simulations, full wind only and thermal only forcing across the transects that separate the basins in units of 10 to the 21 joules per year. So these are all in 10 to the 21 joules per year. The arrows are to scale, and the values are rounded to 1 decimal point accuracy. The transport rates across the Bering Strait are only 1 magnitude smaller than shown. So this is always kind of an interesting place when you look at the heat transport and the general lack of storage here. For example, there are western boundary currents and some storage happening here. So just look at the scale. Again, remember the numbers are not small. 10 to the 8 joules per meter squared per year here, and these are in 10 to the 21 joules per year. So is this the end of the story? Of course not, because you have to again go back and check for dynamic consistencies in terms of sea ice and other things that we mentioned in the abstract, and models will try to take these as constraints to try to look at what's happening in the models, especially CMIP6 models, which are coupled, so it's hard to constrain them. They are going to integrate, they're going to have a drift in terms of the energy budget at the top of the atmosphere, and what the ocean sees, and what the ocean is doing in terms of its heat uptake, heat storage, and transports as well. So this is a complicated problem, but I wanted to include it here just to show that this new paper tries to constrain things much better than has been done before, and provide some new insights into where and how the ocean heat uptake is happening. Southern Ocean playing a huge role in the ocean heat uptake, and North Atlantic playing a role in losing the heat. Indian Ocean contributing a little to the uptake, and a lot of transport from the Southern Ocean into the other oceans to the north. Okay.